tell you something about operating systems, and I'm sure this is an area where you're looking forward. I'm not an expert, okay? I'm not an expert in operating systems, but I'll definitely tell you what I think will be useful for you to know. An operating system is essentially just this, nothing else. And you will see that it's nothing but a piece of software. A whole lot of it is a lot of system software, as it is called. And this system software essentially is a glue. It's a glue between the hardware, computer's hardware, and users. Essentially, it's a glue between the two. So an operating system is essentially a glue which will allow you to use the hardware in the most effective way. And you have different types of operating systems. People give names to it. They say batch operating system, time sharing operating system, distributed operating system, and so on and so forth. Don't worry about all that. They're just some names. Okay, they essentially, you should know that it is a manager. You can think about a bank manager. A manager is the one who interfaces between the users and customers who come to the bank and the employees and the staff who are out there doing different things, right? You go to a bank, one person will be looking at just loans, loan department. One will be just looking at passing checks, and then there'll be one person just issuing cash, right? Have you seen that? Have you been to a bank? Yeah, you see all these things. Essentially, the manager is like an operating system, managing several things, looking at the users, customers, as well as trying to manage the whole functioning of the bank so that everybody is satisfied. So think about something like that as a thing. So if you ask yourself, what is it that an operating system is supposed to do? I've written boring set of bullets here. Okay, don't worry. I think she can come in if she wants to. You're signaling that somebody should come in. They can come in. You can come in. I'm watching each one of you, by the way. Come. So the point is that there are boring set of things that I've written up here, but just get the nice intuition first, okay? So for example, CPU time. If you talk about resources of a computer comprises of hardware, right? Hardware means what? It will have a motherboard, it will have several cards in it, it will have network card, it will have an interface for mouse, keyboard, and so on. And several other interfaces will be there. Then there will be an interface for our famous microphone, then speaker systems and all of that, right? So all of that essentially comprises of different types of hardware which are out there. And then there is a requirement that there is a central computer which is called the CPU. So an operating system has to worry about how to manage the CPU resources. So one of the important things is manager's job is to manage something. So the management essentially leads to managing CPU time, managing memory. Memory is an important thing, right? So you have to manage memory. So memory management, then input output. Anything that comes from keyboard, mouse, and so on will have to be managed as well. And then files and file storage, okay? And then things like the security and as well as the protection of systems out there. And coordinating running programs. Ultimately, you want something useful from your computer, right? So all of this essentially means managing these resources. So what are these resources? As we said, CPU is a resource, memory is a resource, handling input output effectively is an important activity of the operating system, files and storage is an important activity, security and protection is an important thing, and coordinating between running programs are important things. These are the only important bullets. Irrespective of whether you talk of very small embedded operating systems to big mainframe operating systems, these functions will be common to all. Okay, so that is an important thing. So don't forget that. If you know this first slide, you know everything about operating system. You can ask any person you can engage with any of your friends and say, I am developing an embedded operating system. Then you can ask, how are you managing memory? How are you handling input output? How are you handling control files and storage? What is the file system that you have? You can ask these questions. Therefore, these are common across mainframes to embedded systems. Let's look at this hardware and OS. Hardware is the critical, as I told you, it's a glue. The operating system glues users to the hardware and it sits as a glue in the middle. So essentially, an operating system acts as a bridge or a glue between the physical components and the applications itself. If you don't have this link, you cannot do anything at all. Okay, so it's not going to work at all. And therefore, the intermediary has to sit there, has to manage the hardware, CPU, memory, and so on. And it also has to look at the applications. Think about what was developed just now. This Cambrian Spark Zone essentially is an application, right? It's what the user is going to use as an application. So you can think about Cambrian Spark Zone as an application running on top of an operating system. Now you can ask the question whether this operating system is based on, is it Windows or is it Linux, and so on and so forth. So there are applications and then there is the hardware, and in between sits this nice operating system which is gluing the two of them. So it translates essentially high-level software requests into low-level hardware actions. Anything that you want to compute, a user cannot access the CPU directly. It has to pass through the operating system, and the operating system will allot certain CPU resources, and these CPU resources are used and essentially allow you to use it for compute or whatever that you want to do. So these are important actions. Then there are these device drivers and system calls, also very important, and you can be a specialist in each one of them. You can be a specialist. Device drivers essentially are small programs. They are also software, but they are very small programs that allow the OS to communicate with the hardware. Manager is sitting here, which is the operating system, and then there is a piece of hardware. Okay, that link between the hardware and the operating system is the device driver. Okay, very important. If you don't write the device driver properly, you are not bound to have good work coming from that system. You write a bad device driver for a keyboard will not work. You don't write a proper thing for moving some device like a mouse or whatever, that also will have a problem, right? So all these issues are important. Then there are system calls, which are important. These are nothing but APIs, application programming interfaces. You can't talk to the hardware directly, as I mentioned. Hardware is just bare metal, right? It's called the bare metal hardware. You can't be talking to that directly. You have to pass through APIs. For example, take an example of you want to save a file. It calls an OS function. So OS has several functions, and one of the functions is to save a file. So these things are something that are embedded as part of system calls. So the OS uses drivers. Drivers will talk to the disk hardware, and this layered approach will allow you to essentially do all kinds of functions with your system calls. These are important. So device drivers and system calls are equally important, which aid in the working of the operating system and effective usage from user's perspective. Very, very important. Then what are the other components? When you say operating system, you can't be saying something very loose, right? The most important thing is the kernel. And what is a kernel? It is the core of the operating system. And it is always stays in memory of the hardware. If you're running the kernel from memory, the kernel is the one that essentially is the core, and it should run from RAM of your system. Okay? It controls the hardware directly. It manages the CPU directly. It enforces all the protection that is required. You can see now, operating system, very first slide I mentioned a few points. And now you can see what part of the functions of the operating system the kernel is already doing. Can you map it now? You said controls the hardware directly, manages CPU, memory and devices, enforces protection. Go back to the first slide. It was here. You see some of them there, right? So you see kernel is already doing something very interesting, which is part of the operating system, and that's the core of the operating system. So when you talk about kernels, again, you should just know these things. Okay, I can only give you an overview of what these things are. You have what is known as a microkernel and a monolithic kernel. Two types are there. So when you are engaging with somebody, you should be able to confidently talk about it. Okay, you can say you're talking about microkernel and a monolithic kernel. When you say microkernel, it's small kernel, very small kernel. Services are running in the user space. Reliability is good, it's modular, and it has a lot of good features like QNX. QNX is an operating system which is essentially running on microkernels. Okay, that's not what we everyday use. We use Linux, right? Several of you use Linux, and Linux is monolithic kernel. It's a monolithic kernel. All core services run in kernel space. Fast, it can be fast, low latency, and it has simplicity of communication. And Linux is a very good example of being monolithic. So you can stop me anytime if you have a question. I'm more than happy to take you. What are the other components? It's just not about kernel, right? That first slide I told you is the story. And you have to see what part of the first slide, who is doing what. As I mentioned to you, there is a manager in the bank, and then there are staff, right, in the bank. Each one doing some function. We finished one function, we have come to the second function. The first function was the core, and that was the what? What was the first thing we said is heart of the operating system? Come on, guys. The first part that we discussed was just this, kernel, right? We finished that. So you can think about the bank. The first person is now done. We are going to the second person in the bank, and who is going to work with doing a few things more. And that second person is indeed the scheduler. So let's see what the scheduler does. Scheduler manages all the processes and does all the thread management and so on. Forget about all that. The scheduler simply says to schedule. When you say scheduling means who does what first. That is the key. That's all. In one word, who runs to get and when that person gets to run. That is decided by the scheduler. And then you can split the job into several things. You can say creating and destroying processes. You can say switching between tasks. You have task or context switching. Then you have handling inter-process communication, which is an area by itself. IPC is an area by itself. We can be discussing in great details there. Then you can be enforcing priorities. Without this, there can be a contention, right? Many people are trying to use the resources of the computer, particularly CPU. If you did not have a scheduler, people will, these processes have no way of knowing who is to be doing what and when. So the scheduler is an important thing. So here's the important thing. So scheduler takes care of being very, very fair. Says that if there are 4 processes running, how much of thread time, how much of time should each process be allotted is given by the scheduler. So process and thread management is an important thing. Again, going back, first slide, functions were defined. First block was which we understood was what did we discuss the first? Kernel. Ho gaya. Next we are doing scheduler. Ho gaya. Let's go to the third block. Third block is the memory. We are coming to memory. Again, I repeat the same thing. Only first slide is important. First slide is saying when you enter the bank, you see the manager, you see a number of people in the bank. Employees, I mean, not users. All these people, we should know what their functions are, right? So we are describing one person's responsibility. We said check clearance is one, loan department is another, okay, and providing loans to SMEs is another section. Foreign exchange is another section in a bank. All these are different sections in the bank. So each one has a portfolio. So we are discussing different portfolios of the operating system. So this portfolio is memory management. This memory management is an important thing because you can have hardware which provides support for memory management and hardware which does not support. You will be in trouble if your hardware does not provide you support for memory management. There can be memory leaks. So we have to understand crash. You know, the Windows blue screen crash and all that happens because of bad memory management. So very, very important. So what does it do? Key functions are allocation and deallocation of memory. That is, you give memory and remove memory. You do what is known as collection of memory. And that is an important thing. Every time you store something and you finish execution, that part of the memory has to be freed back for the CPU to use. Okay. Usually they use file descriptors to get hold of, essentially these are pointers to different parts of the memory. Unless you release the memory back, CPU will not know that there is available memory for being used. So this is a part of what is known as garbage collection. That is, after you have used, you collect the garbage so that you clean up the memory. A very important aspect. Then you have virtual memory, which gives each process its own address space. You must make sure that each one thinks that this is the amount of memory available for its own functioning. Paging and segmentation is an important aspect, and also memory protection. Make sure that it prevents corrupting each other. One memory should not override the other memory. You can have all kinds of crazy situations if that happens. And why is it important to do this? You have to keep asking this question for everything. Memory management is what allows multiple programs to run safely. If you have multiple programs running, if you don't have memory management, you will not be able to do things efficiently. And that is very important. The same we said about scheduler. Why is this important? Because it is the one that ensures fairness, responsiveness, and real-time guarantees when needed. So, again, go back to the first slide and look at the blocks. We finished with kernel, we finished with scheduler, we finished with memory management. Who's the fourth staff member in the bank? File system management. So this is the next block. All of them mapping back to the very first slide. So what is this guy going to do? File system is essentially organizing data on storage devices. Okay. Responsibilities are creating, reading, writing, managing directories, handling permissions, buffering, caching. All of those operations are essentially part of what file system management is important. And why is this important? Again, I have written it here. The file system gives structure to data. And without it, storage would be a raw. You can't even do anything readable. It will be unreadable. And you'll have total chaos if you don't have a proper file system management part of what the operating system is supposed to do. Many types of file systems are there. ext4, NTFS, FAT32 and so on. These are all important ways by which they organize data on these storage devices. You can be talking about FAT32 storage, NTFS storage, ext4 storage and so on. So these are all different types of organization of the data itself on the storage devices. Very important. So again, kernel is done, scheduler is done, memory management is done, file system management is done, device and IO management to be done. Okay? Device and IO management, this is how OS is going to communicate with the hardware. It includes device drivers, IO scheduling, interrupt handling, and buffering. Anything that comes from outside of the computer comes through these IO managers, okay? Devices and IO managers. So those are the guys who actually will keep interrupting the CPU from its functioning, which means unless you manage these devices and you have proper IO management, you will not be able to service each one of the external inputs that are coming in. So essentially device drivers, which are essentially small pieces of code from the hardware to the CPU, to the OS, is what we defined as the device drivers as an system API, right? System calls I mentioned. So essentially about that. And why is this important? OS abstracts the hardware differences, so programs don't need to know how a device works. So you don't have, programs have no reason to worry about anything with respect to how devices work, just what it does. Okay, very, very important. So I think somebody is talking better than me, so I think should I stop? I can do that, otherwise I'll continue. Okay, particularly from the right side, I see some perhaps more interesting discussions. We can take up that. So we are done with device and IO management. Let's go back and revisit the very first slide. So we said this is an important thing, right? Allocate CPU time, manages memory, handles input output, controls files and storage, and we haven't yet done enforcing security and protection and coordinating of running programs. So we still have to see a few more things. before we understand what are the components of an operating system. So let's move on. Kernel, scheduler done, memory management done, file system done, device and IO management done, and now security and protection. Why does it matter? Because security ensures that programs and users cannot harm the system of each other. And what are the things it's supposed to take care? User authentication, access control, process isolation, encryption, auditing, and logging. If you start becoming familiar with Linux, you'll start coming to know a lot about permissions. You say you have commands like change group, change ownership, then and simple things like you say, I don't know if you're familiar with Linux. How many of you are familiar? No? Okay, great. Chown, right? CHOWN, change owner, change group. You say change owner, change group, and you give 777. If you say 777, read, write, and execute, right? Read, write, execute access to users, to the root, and to others. So you say 777. So these are very simple things. You should just practice them, okay? And that will give you some level of comfort in terms of authentication. Authentication is trying to prove who you are. One of the simplest authentication you can think of is password. Okay, password authentication. Here I am and here are my credentials, you say. So username and password. Things are a lot more sophisticated. People talk about CHAP. CHAP is Challenge Handshake Authentication Protocol. Simple is Password Authentication Protocol. PAP. PAP is Password Authentication Protocol. CHAP is Challenge Handshake. So different sophistications are there even in authentication. Access control, as I mentioned to you. Access control is about change group, change ownership of files and folders and so on, and giving them permissions like chown and so on and so forth. These are important things. Done. Next is networking. Why does it matter? It matters because you're never going to be working alone. You're always going to be part of the larger internet, which means you have to be part of the global system. Essentially, if you have the networking module in your operating system, it is going to implement different protocols like TCP/IP, or it could be talking about HTTP, or the application protocols that you have seen. I'm sure Jamkhandi has written all this, got this stuff done in HTTPS protocol, right? It uses the HTTPS protocol. All these protocols are managed by the operating system in the most effective way because it has a networking component inside it. Managing network interfaces, if you do, you'll use commands like ifconfig -a. You'll see all the interfaces there, right? And then you'll say ifconfig eth0 down. That means the interface is kept down. ifconfig eth0 up. You up the interface and things like that. So very simple commands can be done. You start opening the first book on Linux dummies. Open, try these commands. You will see all the links that I am referring to in all these things. And you must practice if you have to really understand how to use the operating system. And I'm sure you guys are in the AI ML course. It's not so much about the LLMs, but it is so much about using the LLMs effectively, right? And how do you use that? The most important thing is to understand something that starts with the letter P. Prompt engineering. Prompt engineering is a full area by itself. How do you get the best of these LLMs is essentially about prompt engineering. And now you're moving away from that, right? Prompts can be generated automatically and all kinds of things. You talk about agentic AI, right? And all these things coming up. So everything will boil down to knowing all of that means fundamentals should be extremely strong. And that's the reason why this is important. And you'll see a surprise in what I'm going to show you. And I'm sure there is scope for each one of you to have any number of submissions to those websites that Jamkhandi and Madam have started to inaugurate today. And I'm sure you will see a lot of potential there. And things are looking up for each one of you. And so wait till the end before you see what exactly I have. System utilities and user interface is an important thing. Essentially, these components bridge the gap, the user and the kernel. And these include command line tools. As I told you, you create a bash RC file, and inside the bash RC file, you can write the essentially the shell script for automating several operations. Remember, it's always boring to remembering, right? You never remember things. You put everything down in a simple script. Try to automate as much as possible. This automation culture should come to you from day one. Okay, all the things that you want to do, you want to go from one directory to the other directory and go to a particular path, you can write it into a script, and very simple script will simply execute those scripts which will allow you to do things much more faster. And also you have GUIs now, very powerful GUIs, which will let you do other things. People, as I told you in the very first slide, there are so many operating systems and different names. Let's look at the extreme left. The extreme left is an embedded operating system. Now, why is that important and what is that? Are there examples? Yes, there are. Now, having gone through the first slide and all the functions of it, let us see what is it that embedded operating systems will offer for you. They run on small resources. That means memory is very less, storage is less, okay? And also you have to make sure that reliability is very high. And essentially these are small footprints. Fantastic examples exist today. Like you have FreeRTOS, VxWorks, Zephyr. Zephyr is an upcoming operating system, quite popular in the automotive world. If you look at their architecture, they talk about device tree. Do look up, if you have time, in as much detail about Zephyr as possible. Okay? Today I would say that I would strongly recommend you to look up Zephyr. Applications are there, IoT devices, automotive ECUs, medical devices, industrial controllers, wearables, all of them use these embedded operating systems. Is that all? No. Robotic operating systems. Robots, UAVs, land-based, flying, drones, all of them have an operating system equivalent. I'll be very careful, I'm only saying equivalent, because robot operating system is actually not an operating system. It's more a middleware. Okay? They talk about middleware. Essentially, it requires a host operating system. It could be Linux, Windows, and so on. It runs as a middleware in the middle, and it exposes certain things to the users. And therefore, ROS is an important thing. Typical characteristics are real-timeness. Think about it. You're flying a drone, and in real time, you have to take a decision to turn left or right. You can't wait for things to happen at a later instant in time. That means responsiveness of the operating system is important. There are time deadlines after which it does not make sense to even look at the data. You have to throw away the data because the data is stale, and its staleness comes because of lack of real-timeness. So very important as far as ROS is concerned, it's real-time scheduling, hardware abstraction layer, message passing frameworks. Different sensors require access to data to provide you this real-time accesses, and therefore support for sensors, actuators, and AI workloads. All of them require robotics operating systems. Several variants of ROS. You have middleware for Linux on ROS called ROS1, ROS2. You have ROS2 plus RTOS. Okay? Then you have Ubuntu Robotics. Then you have QNX, which is an important thing for autonomous systems. Then you have real-time Linux, which are real-time patches for Linux operating systems. Again, vast range of autonomous robots, drones, self-driving cars, industrial automation, all of them use ROS as an important thing. So each one is tailor-made. Okay? You go to a party, you wear party wear. You go to a college, you wear college dress. If you come and give a lecture, as a professor, I should be dressed properly. Okay? It's important, right? So we have to dress for the occasion, an important thing. Similarly, you use that operating system that is most appropriate for that application. If you're building a wearable, don't use ROS. It doesn't make sense. There's nothing real-time here, right? But if you're using drones, UAVs, land-based, and so on, use ROS. ROS is an important. Choose any operating system which supports ROS, because ROS itself is middleware. Clear? This is important. So keep thinking, what is it that I should do? Which embedded operating system should I choose? Zephyr for UAVs? No. Zephyr for embedded devices. ROS for drones, UAVs, and so on and so forth, if you're building systems. So take care of it. Self-driving cars, industrial automation and so on. And an important thing is happening, and there's a huge shift towards just not using ROS the way you think. They're also percolating into the industrial space. PLCs are coming up in a big way, and you essentially make sure that you marry both of them. So PLC gives you industrial grade reliability. Don't worry what PLC is. There are many expansions to it. What is important is this slide. You mix ROS with industrial reliability. On the left side, you see advanced robotics using ROS, where you have distributed computing architecture, rich ecosystem of tools and packages, and open source. On the right side, you see real-time deterministic operation, high reliability and fault tolerance and safety, and certified systems. Look at hybridization. You use PLCs on one side and ROS on the other. These are potential for applications which you can submit on these portals. If you identify, go to a factory floor, look up PLC operations, use your CS, AI, ML knowledge that you have, and see how you can use these ROS kind of systems and put them together, gives you real magic. Okay? So these are things that you should be very, very open and receptive about. Then you have general purpose operating systems. You know about so many of them. Windows, Mac OS, and all of that. Don't use Windows and Mac OS for an embedded system. Don't use it for a wearable. Don't use it for UAVs. We have already decided that. These are general purpose operating systems. Multi-user, multitasking, rich UI, all these are what general purpose operating systems are all about. Then you have cloud and server-based operating systems. Look at the wide range of operating systems. Same operating system for different applications, for different scenarios, for different kind of situations which we are getting into. Optimized for scalability, networking, virtualization. Linux server and cloud is available. Windows Server is available. VMware is an important thing. And there are other types of operating systems for server and cloud operating systems. Mainframe operating systems. Cloud and server, mainframe. When you say mainframe, you're talking about IBM. IBM mainframes use the mainframe operating systems. Essentially, all this Indigo stuff that you have heard in the newspapers, right? All these airline bookings and all of that. Huge, humongous amount of data processing and all that might be running on, or even government websites, banking, government and airlines, large-scale transactions and all of that. They use mainframe operating systems. The hardware is different. The operating system is a mainframe operating system. So folks, again, remember the party wear, the college wear, the fun wear, wherever you're going, each one of them are different. And you have to choose the right one. And that itself is a very good design choice, right? Choosing the right operating system for the right job. Hope it's not boring, too boring, or is it? Okay. I have a few more slides before we move on, and I'm going to tell you something more interesting. Hopefully that will open up a few other things. You might have heard of virtual machines, right? Have you? Virtual machines, VMs as they call, okay? Again, all of that comes by one magic, which is called the hypervisor. There are open source hypervisors which are available. There is something called Type 1, which runs on bare metal. There is something called hosted virtual machines, which are called essentially which runs on top of a given operating system. VirtualBox, VM. VirtualBox you know, right? It's open. You can download VirtualBox and you can run it on Windows. You want to run Linux? You can install VirtualBox on Windows, and then Oracle will actually release it for you. It's available as free. These are all based on hypervisors. Essentially, virtual machines and operating systems mean you have a host operating system, your VirtualBox, you can run some other operating system on top of that. Everything is virtualized. Virtual means what? CPU is virtualized, the memory is virtualized, hardware is virtualized. They're all physically available as one part. And each operating system is trying to use the same hardware by virtualizing that hardware. Okay, some instances are created which these systems can use. Folks, it's a damn exciting time for all of us, because all this you should know very, very well, thoroughly well. But there are other things coming up. And I'm sure you'll see a lot more interesting things. And hold on till I tell you what they are. But before I do that, let me also tell you the other dimension to operating systems. And this is also an important thing. Energy and operating systems are closely linked. If you don't schedule properly, you will keep the CPU on for a longer time, heating will start, and it will be a lot more energy inefficient. So you have to be sensitive to the fact that energy is an important component. Power bills you don't want to explode. Therefore, managing the computer is the job of the operating system, and the operating system has to be managing such that the energy is kept to the bare minimum. What are the ways by which you do that? You do what is known as dynamic voltage and frequency scaling. You do sleep and hibernate modes, adaptive screen brightness, idle state management, and so on. All these things are important inventions that you have to put in place if you want to build a good energy efficient operating system. So, here's the secret sauce. Have you heard of quantum computers? Have you? Yes. Okay. What is a quantum computer? It's been a recent research highlights that quantum computers are noisy and error prone. I'm not defining what a quantum computer is, but I'm telling you all the problems of quantum computers. They're noisy and error prone, have limited qubit. Instead of bits, you say qubits, right? You say qubits, and have heterogeneous architectures. They require balancing quantum fidelity with versus the system utilization. Because of the above constraints, classical operating systems don't work. And here is where the opportunity is for all of you. Whatever we have studied till now, you should know it so thoroughly that you now say that looks like all that we discussed in the very first slide. That kind of architectural thing actually does not suit very well for quantum operating systems. Is there one at all? Indeed, there is a quantum operating system. And before you go that, quantum computers are fundamentally different because programs are quantum circuits, not instructions anymore. You should know how to write a quantum circuit. Qubits can't freely be copied. You can copy bits, but qubits you can't copy. Execution is probabilistic. Look at the openings that are happening, okay? And hardware is often accessed only via the cloud because to generate qubits, you have different technologies. And those technologies cannot be replicated everywhere. You have to put it in one place and start using them. Okay, qubits decohere quickly. That's another problem. Coherence and decoherence is an important thing. Keeping them coherent for a long time is indeed an issue. So scheduling is time critical. Schedulers are still used, and scheduling is time critical because of decoherence. Look at what you would have studied in your BTech as part of operating system scheduling. Apply those concepts back when you're building quantum operating systems. And keep these things in mind. I'm sure it's all flying for you. You're not following anything I'm saying. I know that. But the point is, if you start thinking now, soon after this lecture, what is this guy was trying to say, Prabhakar? What was he trying to say? Quantum operating system? What are its features? Why is it different from a classical operating system? That's enough for me at the end of today. Think about it, okay? And many things on this slide, I'm sure, is flying above each one of you. Don't worry about it. Very different from classical operating systems because in quantum operating system, you have very specialized system software. Here's what this website that was inaugurated allows you to do, right? You can think about creating a quantum operating system. Manages quantum hardware. Same thing. It's a glue between users and hardware. Hey guys, if it's interesting, you should be talking to each other outside the class. Schedules quantum programs, mitigates noise. Noise, I told you, is already an important problem. And it coordinates between classical and quantum interactions. You can build that glue. How much of classical OS I can use, how much of quantum OS I can use, how to glue the classical and the quantum systems. Must deal with these unique physics of qubits. QoS is a cloud operating system for managing quantum resources. Octopus. Just Google and find out what is QoS, quantum operating system. you'll get to understand what they're trying to build in that. Okay, it's a cloud-based operating system, and this is open source. OQ Topaz is an open source operating system designed for streamline quantum computing operations and so on. Very, very important. Till now we discussed about the functions of classical operating systems. What are the functions of quantum operating systems? You must know that also, right? So now I'll spend a little time, 5 minutes maybe, on trying to tell you what are those functions which you must be able to do if you are building a quantum operating system. One of the things is same thing that we discussed in the first slide. Resource allocation and scheduling, very important. But what is it scheduling? What is the resources here? Efficiently assigning qubits and gates. Optimizing job execution across parallel quantum processors. That is what it is supposed to do. Come to compilation and optimization. Compiles high-level quantum code into low-level gate sequences, and it optimizes for specific hardware. Similarly, hardware abstraction provides some consistent API and so on. Error mitigation and coherence, which is an important correction. Error mitigation and correction is an important thing. Keeping things as scheduling in such a manner that before it decoheres, the qubits get decohered, is an important thing. So scheduling is an important thing, which I missed in the very first bullet here. So error correction and mitigation implement sophisticated quantum error correction codes. So you can put up a proposal on the website and say, I'm coming up with a new proposal for quantum error correction. You can do that. Okay? So building things around quantum computers is an important thing. You're contributing to building the quantum operating system. A very important thing. Okay? Resource management by quantum operating system. Yes, of course. The same resources that we discussed there are appearing here, but they are different resources. Qubits, quantum bits as they call, that's a fundamental unit of quantum information. You're doing quantum operating system, you have to allocate, initialize and all that. Quantum gates and circuits, schedules and optimizations have to be done. Quantum memory and entanglement is an important thing. Entanglement, you know, right? When two qubits are engaged together, you can, if you know one, you'll know the other, and vice versa. Think about so many things. You know the AND gate? You know the AND gate, right? 2-input AND gate. What do? 0, 0 gives you 0. 1, 0 gives you 0. 0, 1 gives you 1, 1 gives you 1. Now, just think about it. 1, 0 gives you input 1 is 1, input 2 is 0, output is 0. I don't have access to input. I only am looking at the output. What do you have at the output? 1, 0 here. What was the output here? 0. Do you know which of the inputs was 1 and 0 by seeing here? Yes, no? No way. In quantum, it's reversible. These gates are reversible. That's the good thing. Think about. I saw some example on the web. I thought it would be useful for me to tell them a little bit about it. You have blue gloves and red gloves. Blue and red. Put them in a box. Put them in a carton. Okay? And shuffle. The way you like, you shuffle. You pull out blue. Do you know anything about the other carton? Yes or no? What is that? If I pull out blue, what is there in that? You know it. Right? That's equivalent of something that happens in quantum. It's in fact entanglement. If I know this, I know that. And if I know that, I know this. Very simple ways people talk about entanglement. See, these things should excite you, right, guys? And this is what is happening. A lot of opportunities are coming up here on this website which you can think of and start doing it. Noise and decoherence is an important thing. Actively mitigates errors and maintains the system coherence and so on. And key components are quantum compiler. You can think of building a quantum compiler. You can be talking about a qubit scheduler. You can be talking about error mitigation layer. You can be talking about resource manager. Anything you want to contribute, these are modules which you can start looking up. Okay, very important. Get inspired that quantum computers have come here to stay. By the time you are in your late 50s, quantum computers will be there. Good to start now. Understand, even if you have not understood this lecture today, if it has sparked interest in you, your Cambrian spark is done, right? I've sparked it. Go ahead, read, understand, and go ahead and build something. What's the big summary? The big summary is OS concepts and knowledge are never going to get obsolete. Never. If you have studied about OS and its concepts, whether it is a classical operating system or whether it is the quantum operating system, these concepts are never obsolete. OS function is the foundation for building applications. Compact and fast, energy efficient, portable are all features which will let you build for building applications. There is a worldwide interest in developing operating system for quantum computers, for sure. And I hope that this has sparked enough interest in you to go and at least read, understand about quantum operating systems. Maybe there is a simulator. I think I saw a simulator on YouTube and a description about that. Download it, use it. I'm sure you'll understand a lot better. Thank you guys. Thank you very much.